Okay, so this particular video is going to serve as a quick review. It is stuff we should already know from general chemistry, and so keep that in mind. We will be moving quickly, and we won't be covering things in too much detail. So if you have any questions, feel free to ask me, and then I can either help you with that, or I can kind of guide you and give you some information or some resources to take a look at the stuff that you need. So here's the periodic table. We're all pretty familiar with that. Just to kind of go over some quick vocabulary and some things like that. We got carbon, for example, on the periodic table. It's got the 6 on top. That's the atomic number. And below is 12.01. That's the weighted average mass. So that's the atomic mass of carbon. And we say weighted average because it's the average of all of the isotopes that are on Earth. So we can also write elemental symbols like this with the atomic number on the lower left as the subscript and then the mass number as a superscript. Okay, so this is an example of carbon 12. And so remember, the nucleus is composed of protons and neutrons. And this is actually something I've been trying to teach my son for a while. He's 4. And I ask him, a nucleus is composed of, and he tells me. So we're on the right track. So hopefully you guys remember that now. The atomic number is going to be the number of protons, and then the mass number is going to be the number of protons and neutrons combined. Okay? And so that's actually going to be really important for when we're discussing isotopes, which we'll get to shortly. But just to go over a couple other things, the neutral elements, so for example, for neutral elements, the number of protons is equal to the number of electrons, okay? And so this is because the protons are positive and the electrons are negative, right? We have to balance out charge, which makes it neutral. And all elements, elemental things are going to be neutral. And so going back to carbon, we have 3 different ways we can draw carbon, right? We got a carbon with the 12, 13, and 14 in the superscript on the left of each atom. And these correspond to carbon 12, 13, and 14. So I'm not sure, you're probably familiar with carbon dating, but maybe you didn't know that carbon 14 was what we use for carbon dating because it's radioactive and it has a specific half-life that we can use to kind of figure out how long it's been around. And so isotopes are what these are. These are different isotopes, and they have the same number of protons, but a different number of neutrons. So remember that mass number on the superscript on the upper left, it corresponds to the protons as well as the neutrons. And so they all have the 6 protons because that's what defines carbon as carbon. But that different mass number is because they have different numbers of neutrons. So it could have 6, 7, and 8, respectively, for 12, 13, and 14. Carbon 12, 13, and 14. Some other really cool isotopes that I want to bring up are, we're already aware of hydrogen, right? But hydrogen with a neutron is also known as deuterium, abbreviated with a D. And so D2O, like water with a deuterium, is actually heavy water. It's called heavy water because it is heavier, right? Neutrons add mass. And the cool thing about heavy water is that once it's frozen, unlike regular ice, it doesn't actually float at the top. It sinks in water, which is cool. And then another really cool one is the tritium isotope for hydrogen. This is a really cool, I like this one in particular because it is actually radioactive, and a buddy of mine has actually a pretty cool gun that has tritium sights on it. So it actually glows because it's got tritium on there and it's radioactive. So just a little fun fact about that. Now, another example of an element having different isotopes is lithium. So we can have a lithium 7 and a lithium 6, for example. They both are defined by the number of protons, which is 3, and so they are lithium elements. But the lithium-7 isotope has a 92.4% abundance, whereas the lithium-6 has a 7.59% abundance. And that's what ends up giving you that average weighted atomic mass of 6.94, which is closer to 7 than it is 6 because there's 92% of 7. So the reason why this one is really cool, I guess it's more of a side note than anything, just to kind of draw you into the world of chemistry. I like lithium in particular because, or just wanted to bring it up because it was actually in 7-Up. And fun fact about 7-Up, it's called 7-Up because lithium citrate was added to it in the early 1900s. And lithium is used as a medicine, right? It's to prevent mania. So for people that have bipolar disorder. And so that's why it was called 7-Up, because it kept you up and happy and everything was all good, right? Because you had the lithium in there. It's an actual drug. So really, that's kind of why I find it funny or interesting. And as I showed you above, 7 corresponds to the larger abundance of lithium-7, or corresponds to the isotope lithium-7. So also, a little fun fact, over the spring semester, a student of mine was in Mexico during the isolation, and she sent me some pictures of a soda that she got at a store there, and Peña Fiel, and it actually has litio in it, which is lithium. So it's also got these cool, I love how it has all the ingredients in Spanish, and then on the other side of the bottle it has their molecular formulas actually drawn out, but it's got lithium in it. That's crazy. So just be careful what you drink when you're in other countries. Long story short, right? Okay, so back to chemistry that's in our book. Basically, the periodic table, right? So remember, again, a little bit of vocabulary for it. As we go across a row, like from left to right, for example, that row is called a period, okay? And then if we were to go up a column or down a column, the columns are actually called groups. Okay, so let's go over period 1, 2, and 3, for example. Some information with respect to those is the molecular or the atomic orbitals. So we have a S2, that would be a completely filled s orbital in period 1, S2p6 for 2, and S2p6 for 3. But also remember, row 3 has those d orbitals. Okay, and so the period 1 is the principal quantum number n, which is kind of like the first shell, then 2 is the second, and 3 is the third. So it looks kind of like this little planet with rings around it. And then we have the electrons residing in those different energy orbitals. Okay, and just remember also that S is the lowest energy orbital and is closest to the nucleus, while P is just higher in energy than the S. That's pretty much all we need to know about these guys. Just a refresher as to what they look like. So remember, the s orbitals are spherical, while the p orbitals look like dumbbells. So they got the upper and lower lobe. Oftentimes you'll see them with different colored lobes. So one of them shaded in, for example, and the other not. And then also remember that there's 3 of them, and there's a px, py, and a pz, which means that they're projected in the x, y, and z plane, respectively. Okay, and so moving on, remember valence electrons. We're talking about these orbitals and the different energies, right? So valence electrons are the electrons in the outermost shell. Okay, and so these guys are important because they are the ones that are doing all the chemistry that we care about, right? Those are the ones that are making the bonds, and those are the ones that are reacting and kind of giving up electrons and taking them, or, well, I guess electrons aren't taking them, but you get what I mean. So that's pretty much why these valence electrons are so important, because that's what we're working with this whole time in organic chemistry. And so also remember that the group numbers correspond to the number of valence electrons. And so we have group 1 right above where hydrogen is, and then group 2 where beryllium is. We're going to skip the transition metals and then move on to 3, 4, 5, 6, 7, and 8. So they are oftentimes referred to as like 4A or 14, but we're just going to simplify it to just 4, 5, 6, 7, and 8. And remember, these groups, that tells us that the atoms in that group have that many valence electrons. So hydrogen has 1, beryllium has 2, boron has 3, so on and so forth. And this is going to be important for when we want to draw structures like Lewis dot structures and find out formal charges, etc. Okay, so while we're on the topic of bonding or Lewis structures, let's talk about the different types of bonding or compounds that we can form. And so we've got covalent bonds or covalent compounds, and we've got ionic bonds or ionic compounds. So remember the difference between the two. Covalent compounds are formed by sharing electrons, and ionic compounds are formed by transferring electrons. So that's covalent compounds when you have a small difference in electronegativity, while ionic compounds is when you have a large difference in electronegativity. Ionic compounds are typically going to be between metals and nonmetals. So remember, on the periodic table, metals are on the left, nonmetals are on the right. And most of the periodic table consists of metals. Covalent compounds are nonmetals and nonmetals combining. And that's basically all the stuff on the right side, right? So an example could be H2, hydrogen gas, or ethane, CH3, for covalent compounds. And then ionic compounds, remember, to pinpoint those, you just look for a metal, right? So lithium bromide or sodium amide, NaNH2. And then another sodium atom present indicates that this O2CCH3 is a negatively charged thing and is a salt as well, or an ionic compound. And so remember, the presence of lithium, sodium, or potassium, or whatever, that it screams out ionic compounds. And remember, when we write them in some molecular formula as they are, they're neutral, but in actuality, we can split them up into lithium and sodium plus, as well as bromide minus, and then NH2 minus is an amide, and then O2CCH3 is actually a carboxylate, which we'll become familiar with later. I just wanted you to see it now. Okay. So pasting the periodic table here for you again. When it comes to the periodic table, let me paste this real quick. We have hydrogen and helium. And remember, the electron configuration for these is 1s1, and then for helium is 1s2. So row 2, we've got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, the noble gas. He likes to be hanging out on his own, so I'll put him up here. Why not? So for the electron configuration of these, we are in the second row, and so now we've kind of filled up our 1s orbital, and so we're working with our 2s1, 2s2, 2s2, and then once we fill up that s orbital with 2 electrons, we can fill up the 2p orbital, right? So for boron, we got 2s2, 2p1, carbon, 2s2, 2p2, so on and so forth until we get to fluorine, which has the electron configuration of 2s2, 2p5, right? Because it's got 7 valence electrons. And then looking at neon, this has the electron configuration of 2s2, 2p6. So I purposely left out the 1s2 on all of these just for simplicity. But notice neon has 8 electrons in its outer shell. That's 2, the principal quantum number 2. And everything wants to achieve that octet, right? Remember, we always want to be like the noble gases and have 8 electrons in our outer shell, or like helium, which has 2, or hydrogen wanting to be like that guy. And so um, this is, again, just a review, so moving over it very quickly. If you have any questions, obviously let me know. So just for your information, remember the groups correspond to the number of valence electrons, right? Uh, but when it comes to bonding, highlighted in red, 1, 2, 3, and 4, those groups, the number of bonds is equal to the number of valence electrons. So this is pretty useful, right? And I'm going to abbreviate valence electrons as V e to the superscript with a minus right there, just to make it easy. That's how I do my electrons. And then for groups 5, 6, 7, and 8, the number of bonds is equal to is equal to 8 minus the number of valence electrons. And obviously this is different than the other ones, but it's just something we'll have to remember, or we'll just eventually just be really good at it and not have to think about it at all, which is where we want to be, right? Okay, so time for practice. So hydrogen has 1 valence electrons in group 1, and another hydrogen atom coming together makes elemental hydrogen. That's H with a single bond to another H. So the point here is that it's in group 1 and it has only 1 bond. So beryllium is in group 2 and it has 2 bonds. Boron is in group 3, it has 3 bonds. Carbon is in group 4 and it has 4 bonds. Okay, so these are the ones that were written above in red, and now for nitrogen, remember, that was in blue. That has group 5. It has 5 valence electrons, and the way to figure out how many bonds it's supposed to have is do 8 minus 5, and that is 3. So nitrogen commonly has 3 bonds. And then remember these 2 electrons here, the lone pairs there. And now for oxygen, we can pretty much do the same setup, right? We have oxygen in group 6, it has 6 valence electrons, and so we do 8 minus 6 is equal to 2. So it has typically 2 bonds, right? And this is water. We're familiar with that. Now, looking at fluorine, it's in group 7. It's got 7 valence electrons, so whoops. 8 minus 7 is equal to 1, so the halogens typically form 1 bond, and that is what we have here, HF. This is actually hydrofluoric acid. It's what they used in Breaking Bad to dissolve the body in the bathtub. Not real life, but interesting story, right? Now neon is in group 8. It's a noble gas. 8 minus 8 is 0, so that's why it doesn't form any bonds. Okay. So notice I've drew all of these electrons kind of on the atom, on the outer part of that. Remember, these are non-bonding electrons, and they are also known as lone pairs, right? All right, so that's pretty much it for the review on the periodic table and like a little bit on the bonding. We'll go over some more bonding later, but go ahead and try some of the practice problems, and that's it. Let me know if you have any questions.